the link prediction can be used to create a recommendation system. A recommendation system is a system that would assess the score, the rating of the whether you like this movie or not based on the past records, right? The past record that you have with the movies. So think about the data that you play with in the topic modeling. Like in the topic modeling, we have that Ajahn Ta taught. There's this metrics that the users watch movies and give the score. Based on that score, you can assess the topics that users like. Similar thing can be done here. It's actually the same thing. It's like you are trying. So if you think about it as a graph, you are creating a connection between that person to the topic, right? Between that person to the topic. So it's like a bipartite graph that you have people on one side and the topics on another side. Okay, so that means link prediction in metric decomposition is basically the same thing as that. And we can explain it mathematically here, and then looking at the implementation of the recommender system that utilize this very technique. So in that sense, we want to, if we have an adjacency matrix A, right, we want to modify A, modify the source, right, the source adjacency matrix, and get the target adjacency matrix that is closely approximate to the source somehow, right? So we want to find the minimization between these two, right? The f of the source, a source, and the target of the thing that you want to predict. So we need to have the training data set that this is how the connection is done, and the source data input that we have, like the surrounding metrics, giving some function that need to be learned. We want to minimize this, okay? And this can be done by, if we take a look at this using metric decomposition, we can decompose metric A into A and then sigma and then U transpose. This can be done because the matrix A would be a square matrix. Here is a square matrix. Unlike in topic modeling that you have the rectangular matrix, A is a square matrix that allows it to be decomposed into the eigenvector in row and eigenvector in column using the eigen decomposition. If we from this one, we can, if we take a function to A, is similar to take a function to the middle one, which is the eigenvalue. This would be a diagonal matrix of the eigenvalue. We can do something like a scale of values here, or this would be the prediction function that we want to perform. Okay. And that would mean that we can change from FA into the U and then F of the diagonal matrix and then U transpose minus A of the target. And this would equal to this one, equal to finding F, finding the function by minimizing the target that we want, the training data set, and the decomposition of U from the actual data set, and optimize this out. So this would be the regression values. So framing this problem in different realm would be something like this one. We want to predict the expected rating. We want to find the expected rating, RUI. This RUI come from the QI times PU. What is QI and what is PU? If I were to change back to which one should be the best one? So this is the value that we want to predict. The value we want to predict is the Q times PU. What we want to do is to optimize this one. You can see the similarity between this equation. This is the equation of the recommender system. In the recommender system, the idea of the system is to predict the rating. And the rating comes from the user vector and the item vector, right? You kind of multiply them together and then get the rating value. But these two, we still do not know, and it need to be learned. Okay, it need to be learned that how to do that. It is done by minimize the qi transport dot pu with the rating, right? RUI, and then we kind of minimize the square error here. Square error is the same as the previous sum here, error, minimizing this function. So from this, you can see here that this is the same thing. Now you kind of using U transpose here, and then dot it to the QI here for each of the value that you have in the rating, right? And then minimize them to get the QI and PU, right? And then PU out. So this is the problem of recommender, okay? And how does it work in the recommender? Framing it as recommender would allow you to understand easier than the matrix decomposition part, because in most of the sources I find, they talk about matrix decomposition, but they did not say things about how the optimization is done, which is a little bit troublesome because it will make it difficult to imagine how to estimate that. But by framing it this way, now we know that we want to find the value of PI and QU. PI and QU in total sense would be this matrix, right? The U and U transpose, just like the two, right? But we talk about, and then we dot them, we will get that. We will get the projection. We have this RUI as the actual rating, and then we want to learn the QI and the PU. So this is the basic value, but there are certain auto factors that can be incorporated into this regression problem. One of which is the regularization. Regularization can be incorporated as the term about the values. So that means in this, you need to minimize your P and Q by minimizing errors plus the regularization terms. The regularization terms here is the L2 regularization. That means the value should not be so large. This would, in optimization, this would reduce the value of Q and P to be low value but not zero, right? So this is how regularization is done. For the bias, because for example, if I were to be an optimistic person, I would kind of give high score for every movie, right? I would give high score to every rating that I have. And that is the bias, right? Or some movie will be very terrible, right? And it gets kind of low score for the whole things. And that's also bias in terms of item and bias in terms of users. So this bias can be modeled in the rating itself by having this QI and PU plus mu, which is the entire rating. Like usually people used to give 2. So 2 would be the mu I. And BI is the bias in item and BU is the bias in user. So bias in items like on average, this is the average rating. In terms of user, on average, the user would give this average rating. Right? So combine the whole thing, you get the predicted rating out. Right? So now we have the full form of the optimization model that need to be optimized. First, we have mu. Mu is the average value. BI is the average value of the item I minus mu. BU is average value of item user U minus mu. And the PI, QI, and PU are the values that you want to optimize, right? And just that. This can be optimized using HGD, right? Just take the derivative of that. And then you get the gradient, and that gradient can be used to optimize with the stochastic gradient descent, like in the what Ajanta taught in the early lectures, or what some of you have done in the deep learning class. Okay, so SGD, stochastic gradient descent, It works by sampling data set and then use that to optimize by adjusting the sample data, use the sample data to calculate gradient, and then use those gradient to update parameters and keep doing that for a lot of time, and you get the values that you got, right? But instead of doing that by your own, just like in Keras, there is already a platform, right, that we can use to make the decomposition prediction like that. This is a library in Python called Surprise. It's actually, I don't remember the names. It comes from something like recommendation somehow here. Python scikit for recommendation system. Don't ask me how it called Surprise. Okay, so it has this ready-to-use prediction algorithm based on something like SVD and MF, which are metric decomposition, metric factorizations. So you can use this recommender and think about them as the graph, as the bipartite graph that you want to find the connection between people and item, right? You want to find connection between the two. Right? So now we will take a look at how you can do that in Python, all right? And then we come back to the issue later on. Okay. To do that, you need to install the surprise lib. You can watch me first and then try it on your own later on. And then maybe you can do a lot more other things. There are other function or other parameters that you can configure. You can use KNN, which will just pick up the nearby neighbor and use that to make justification. Right? Nearby neighbor make justification. Oh, just like common neighbor, right? Or you can use this SVD, which will do the decomposition and optimization of the rating. Okay, so here are the example. Let's start with this one. I did not have my own data set, so I load the movie lens 100K, which has the Surprise has this data set, which will download that automatically to your computer. You need to connect to internet, well, but you connect it right now, right? Otherwise, you cannot watch me here. Come on. I forgot to install Surprise here as well. Bad. Let me do that. I did that. I prepared this lecture on another computer on the Mac, but well, it's another computer. Let me find that. Installation, Conda Forge, Surprise. Let me install the library for a minute. Done. Yes. Finish. Right now, here. So in these two commands, the first command will load the ML100K. So yes, I want to download it. It will download ML100K. And the second command will build the full trend set. It will build the trend set from the data that we have here. From the, then I will get the trend set out. Here, it's done. Put it here. Now let's take a look at the data set first, and then we'll create a model and then fit the model and then perform prediction later on. So we take a look at the rating data. It is in this form. It is in like this 0 to 0, you get 3, 0 to this, you get 4, 0 to this one, you get 4. So by this, you now see that they are very similar to the Facebook data that I showed you earlier. But instead of having just connection, you have the quality of the connection as well. And you need to realize that the first and the second are not in the same layer. They are a bipartite graph, right? They are like connection from one layer to another layer, right? One layer to another layer. So they are bipartite graph. Okay, so by iterate through the all rating, we have the rating. You can view the raw rating, which will give you the raw rating and something like timestamp ID here. And you can look at UR. UR is user rating, which will give you the rating of each user. Basically, this is just a set of a data structure that combine together, and then it will be used to in the building model later on. So to build the recommender using SVD, is actually to find predictive link in the bipartite graph, right? We can use the SVD function and then fit the data set into that. You can take a look later on in the documentation. There will be a way that you can read from data frame and then import that as a set into this as well. So here I already build SVD and then fit the data set into that. In prediction, this is the function build entire test set, which will build a kind of actually test sample for us. And then we can use recom.test to test that, which will make prediction, and then we can check the prediction there. Here. All right. You see that here the RUI equal 3.529 all the way through. What does that mean? RUI equal 3.529 here. This is an average rating, right? This indicates that because we use like build entire test set, and if you use build test set, it will build a test set which you can compare the rating. Build entire test set will give you. Wait, actually, I should use. Right, build test set. Okay, now we have comparison. Using build test set, it would kind of sampling data from the whole things, and then we get the test set here. The test set will be like part of the data set that is not used in training. And in comparison, you can see that RUI here will be the rating, and then you can compare between them and compute the error. Why on the other way, if you build entire test set, you can think of the prediction set like this one. Prediction set is a set of like the edges that has not been found. So link prediction meaning we are ranking this on which link should be up first. Take a look at that later on. Okay, so by having this actual RUI and the estimation, we can compute the accuracy. This accuracy would indicate the accuracy between the rating, the actual rating, and the estimated rating. Okay, so we have the two matrices here, the RMSE root mean square error, which is the root of the mean square error, and the mean absolute error. Right, so I will write the full name here. The RMSE is the root mean square error, while the MAE is the mean absolute error. Right, these two. I can probably write the LaTeX here to get you the equation, but I figured I could just write it using this one. Okay, so the RMSE RMSE. This is the root of the mean square error. So this is the root of the mean of the summation of the rating, actual rating, right? Minus the predicted rating. Okay, for each of the I. Okay, so this is the root mean square error. Yeah, this is the root mean square error. For the mean absolute error, this is the mean of the absolute error. I need eraser. Absolute error. Right, so these are the two, root mean square error and the mean absolute error. So build test set give you the test set, while build anti-test set give you the unknown link. That's why when you use, let me remove this is all. Let me clear them. Clear. Clear. Okay. Okay. Why? So if we use the recom.test with the prediction set, no, prediction set. It will give you the prediction of the unknown links. And from this on, we can use the estimated values to rank the similar, you can think about them as similarity, to rank whether this person should connect to this movie or not, and use it in recommendation. Right, so there are issues in the link prediction as well as in recommendation. You can actually, the issues are the same for both. First one is the cold start problems. In the cold start problems, if you have a new person coming into the network without any connection, how can you connect that person to another? Right, so cold start problems can happen either for the item levels or for the user level. Another that's one problem that is really classic in either recommender systems or using the link prediction as basic link prediction, because cold start problem means that you cannot find the connection, you cannot find a common neighbor. There aren't any common neighbors. So yeah, so that's the problem. Usually to solve the cold start problem, you need to make a random suggestion link, maybe coming from the hub node or coming from randomly selected people that you think might be around that, using Bayesian technique to find the likely connection using some types of probability. Right, so that is the first issue. The second issue is the fluctuation of the network. In the social network, the link can be created or destroyed. Like you can unfriend your friends, right? You can be connected to a person for a certain time and then not, right? And new node also come in and out. That means the network changed by time. Evaluating the link prediction at one time will valid only just for that data set because the network will change. Okay, so that's another problem here, the temporal network. And the last one is that the link prediction that we have here, we just trying to look at the connection. But if the link itself has certain nature, that's not just the weight, not just the value, but it also has the something like you have the negative of polarity. And so that will make things further complicated. You need custom-made algorithm in order to address that problem, right? So in summary, so what we have learned today is a way that you can connect between nodes. You can use that to connect. If you crawl data from Pantip, you can connect person an account to an account to see whether there are certain type of connection between them based on the post that they engage, based on the similarity if you use text mining as well to indicate that they are similar to one another. Okay, you can use link prediction to, as you can see, draw relationship that may have been there, but you do not know whether they are there. You can use them to make suggestion to the your application to create to expand the network to go further.